now James Brownridge, and he will tell us something about freezing of water.
Right.
Yes? Okay.
Good morning. I would like to thank Jerry and the organizing committee for inviting me. I hope to put on a pretty good show this morning. There's been some effort to get young people involved in these water experiments, so I have a suggestion that I hope will generate at least one question after my presentation. For most of you here, I would suggest maybe your grandchildren, but even if you have your children, label a bottle of unopened water with a date, set it on the shelf, and leave it in perpetuity, and ask them to explain what has happened after 6 months or 1 year. If you happen to have a kitchen scale, they may take it off and weigh it from time to time. Now, to move on to my presentation, if you read my abstract, you notice I say nature often tries to communicate with us, but we are not listening. I try to listen to nature. Nature has informed me that this should probably be the last time I present at this conference, and that maybe I should stop doing technical experiments and maybe write up some of my current results. So nature told me this after I wrote my abstract, so I have made some modifications. I would like to summarize my contribution to water science since I started working in this field maybe 20 years ago. So you will see some old slides and a few new slides, and I will also attempt to point out where I think progress can still be made, and people may want to pick up on some of the stuff that I've done. So I initially planned to talk about my work with electrical activity in water, but now I've switched over. I will just mention a little bit about it and review other contributions I've made. To look at electrical activity in water, we need a very simple setup. And I am talking about all of my work with respect to water is tabletop physics or tabletop experiments. You can have your children or grandchildren do some of these experiments at home with little or no equipment. But anyway, this is the setup to measure initial electrical activity in water. So I take a sample of water in this column here, this tube, and start lowering its temperature. I am removing energy from the water until I get to 0 degrees Celsius. And below 0, I am now storing energy in water. At some point, that energy will be released as latent heat, and the temperature of that water will rise to 0. When this happens, there's an electrical EMF signal produced, which is very strong. Recently, I read a paper by Jerry and his group where they looked at the infrared IR pulse produced at this point in water. This is pure water, and this is what the electrical signal looked like. We're going into solid ice here. This is a kind of a prime example. You need fairly pure water. In my case, I use double distilled water. Now I use dirty water, and this is water, looks to the eye is the same, it's crystal clear. I mixed in a little bit of clay, centrifuged it, filtered it, and then went through the same process. And now you can see the tremendous electrical activity. The initial EMF produced when it latent heat was released. During the whole time of freezing, there's a voltage produced, a potential. There's current flowing through the system until it finally freezes and go into solid ice. And then during the melting state, it's fairly constant. Now, my initial implication of study was see, do I see a pattern that's unique to the contaminant that's in the water? So again, I used clay, which we find in the natural environment, and made three simple experiments, cooling samples, and you can see the patterns are similar, but they're not exactly the same. So my intention for this experiment was to continue this process to see if there was a unique pattern depending on the contamination in the water, although the water physically to the eye looked to be clean. And again, I'm moving rather rapidly because I want to kind of review the history as I mentioned before. So now I put water in a confined tube, maybe 3 to 4 millimeters in diameter. And that's what happened when we freeze the water. Went the wrong way. You notice I put the word memory in here. In this case, I'm not referring to the memory of water, but when I freeze the water and put my electronic measuring device just on one end of the water, the signal I get out is always the same. In this case, it's positive, 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 positive. Somehow, I've gone through freezing, thawing cycles, lowering the temperature, raising the temperature, lowering the temperature, raising the temperature. The EMF, I forget, is the same polarity on the end of the crystal, not the crystal, the end of the water tube. I reverse it, and it's the opposite polarity. I reverse it back the other way, and it's back to the same polarity. I can do this today, tomorrow, and so forth. Now the question is, how does the water know which end to polarize? Which end should be positive and which end should be negative? I'll have an indication in the next slide. So I put the water now in a larger container. And all of a sudden, I see frustration. One end, once it's positive, it's negative, positive is negative, no polarity there, no consistent polarity. It's just up and down as the freezing process takes place. Where previously, it was all in one pulse in one direction. Now that was the electrical activity in water, which I plan to pursue. I will refer back to that later on when I start talking about clusters and why this may be. But now moving on to supercooled water. I should have mentioned earlier, I will be showing some new slides and some old slides. This is the old slide that I showed at a previous presentation. If you read the textbooks and the current literature, it's always talked about if you want to supercool water, it must be clean. That ain't so. All water will supercool, no matter how dirty it is. A water compound, so you can see what I have listed here, milk, orange juice, all of them will supercool, and they will supercool repeatedly. There's one condition: it must be still water. You can't be shaking it. If it's still, it will cool below zero before it freezes 99.99 times out of 100. This is yesterday. I went on a tour to the museum. Running through puddles of water, I got wet. Seriously wet by my standard. All of that water was collected in the container. It will supercool. This is really dirty, muddy water. We are walking on campus through it, collected, and this is the backup. This is the typical cooling curve. It cools to -5 degrees before it's freezing. But there's in the general public, there is a contradiction. You will walk out in the morning, the temperature will drop just to 0. You will see ice. In this part of the water here, you will see ice. If the day before you had collected some of that water, put it in a container and sealed it, and left it in the same pool of water here, it would not have ice in it. It would not have frozen. Where the water in the open to the atmosphere will have ice crystals. I'll get to why that is so in a jiffy, in a minute. And the answer is because in order for water to freeze, still water now I'm referring to, so you should keep that in mind. I'm not talking about flowing water or shaking water. In order for water to freeze, there must be a catalyst or a nucleation agent in the water if it's above about a minus 40 degrees Celsius. There absolutely must be some agent to initiate freezing, otherwise it will not freeze. In this picture, I showed where the nucleation agent is. The water begins freezing across. It may be anywhere in this container, on the surface or in the center of the water. The same thing here, and the time it takes for the water to solidify depends on how low it supercools. If it supercools to 2 degrees, it may take hours if it's a container of water the size of this ball we're working with here. If it cools to 20 degrees, it may take 30 minutes. If it cools to minus 30 degrees, which is very unlikely, that would be a small sample, it may freeze solid in 5 minutes. But it all depends on how deep the water supercools as to how long it will take to freeze. Again, I'm cooling water very slowly, not very deep, and looking at the electrical activity. So I've got this tube of water. I've got a thermocouple somewhere on the tube. The initiation site may be at the opposite end of the water. So I will get this electrical signal when the latent heat is released, but I will not see a change in temperature in the water where my thermocouple is located. In this case, it's up to 3 minutes. So freezing may start, but depending on where you are measuring, you may not detect it for some considerable time. Nope. What did I do wrong? Now, I mentioned that water will not freeze unless there's a nucleation agent in it. There's much controversy about this, and I've received considerable feedback saying, you don't know what you're talking about. This was early on in my works. So in an attempt to confirm this, that water will not freeze until it cools to the temperature specific to the nucleation agent in the water, it will not freeze. I decided to seal water in a glass tube, in a whole series of glass tubes, and for each one of them, I determined where the specific temperature was. In this case, for this case here, it was about minus 17 degrees. So I cooled this water down to 15 degrees and held it for 422 days. I think that's a world record. I can't prove it. And after 422 days, I went around the department and had people take a bet on a cup of coffee of how long I could keep this cool, the whole department. And one person said forever. And he said forever because that would guarantee that he would win. Anyway, after 400 and something days, I cooled the water down to minus 17 degrees, and bang, latent heat was released and the water froze. I went back a year later, the same sample of water, and this is that particular run, cooled it down to minus, what I have over there, 14 degrees. Oh, one reason I'm having to retire is my vision is deteriorating, so if I quoted the wrong number, let me know. But anyway, so I cooled it down and held it for several hours. Then cooled it down to the temperature, quote, that I knew it should freeze based on the previous information. Lo and behold, latent heat was released and the water froze. I still have this sample, and I predict I could go back today and put it in the system, and the same thing will happen. This water in this vial will not freeze, or latent heat will not be released until I get down to minus 17 degrees. So that is unique to the nucleation site in this water. Now, if I take this vial and vigorously shake it, it's a possibility that I could change that. And I'll get to that in a minute, why that is the case in a minute. But there's probably a 50-50 chance that nothing will change. It depends on what that nucleation site is. Now, there's one perfect nucleator in nature as far as I'm concerned. That is ice crystals. Water will begin to freeze at 0 temperature only if there's an ice crystal present. So the reason you go out in the morning and find frost on your car, or that puddle of water I talked about had ice on it in the morning and this morning, and the temperature was right at 0 or just below 0, it's because from the atmosphere comes ice crystals falling down. They interact with the surface of that water, and the reaction takes place. Crystallization begins, and it continues to grow as long as you're below that temperature. This is an experiment to show that. In the case on the right over here, I covered that's liquid nitrogen in a styrofoam cup, and if you've seen liquid nitrogen in a styrofoam cup, you see fog or ice crystals falling down. So I can cover and uncover these two containers here. So I uncovered both containers on the left here, both containers, the red and white one, started cooling down, and lo and behold, as soon as I got to 0, freezing began. And now we're solid ice. Repeat the experiment, but cover the red, cover the green side, leave the red side open. Look at what happened. The red freezes exactly like 0. The other side goes minus 5 degrees or thereabouts, and later on nucleates when the water temperature falls to the specific temperature that the nucleation agent will initiate freezing, and it begins to freeze. And you can repeat this experiment over and over and over and over, and you will get the same results of freezing here. You may not get the same results of freezing on the open one because the new nucleator may have entered the water, and it may have a different specific freezing temperature. Moving on rapidly. Now, I'm not on social media per se, except I have a website. Most of my communication is with young people, at least 50%, maybe a little bit more than 50%. Write me from something they've read, or that I've written in something, and we communicate back and forth. So I am trying to encourage the young people to get involved. But the huge elephant in my corner is I started in water because a colleague asked me, does hot water freeze faster than cold water? I said, yes, everybody knows that. He said, why? I started waving my hands and hear me, and couldn't. So I decided I wanted to find the answer. The why. Not that it does, because it will often freeze faster than cooler water. So we're still fighting this battle, and this is a major battle going on now, intellectually. And the answer is, it really can freeze faster than cold water under certain circumstances. This is a demonstration of it. This is water sealed in glass tubes. Heated to more than 100 degrees, and yet and the other water is very cold, below 0, but yet the hot water is solid ice before the cold water. Special circumstances. If you're not paying attention, you say, oh, eureka! I just proved the theory that's over 2,000 years old, that hot water will freeze faster than cold water. Yes, but it has absolutely nothing to do with fundamental properties of water. It's the circumstances, the environment. Proof of that, 4 tubes of water. as identical as I can make them. Too hot, too cold. Look at what happened. In one case, the hot freezes before the cold. The next case, the cold freezes before the hot. I have been asked to review many papers, and where they've claimed there was a crossover, the hot freeze before the cold. Here's proof. I said, convince me if you have identical conditions. Newton's law of cooling is rock solid. The requirement is your conditions must be identical. Then the hot water will never, it's impossible, to cool to zero before the cold water. Now the hot water may freeze to zero before the cold water, but only because of that agent in it at a specific temperature that dictates freeze at -2 degrees, where the cold water may have an agent in it that freezes at -10. In that case, the hot water will always freeze before the cold water. So you can set up a circumstance, which I did, where you can guarantee that the hot water will always freeze before the cold water. Now back to the nucleation agent. This is a sample in a sealed tube again where froze water continuously, and this is published, this is old slide, this is published results. And this glass vial had consistently, latent heat was released consistently at -14 degrees. So I pulled it out, put it back in the system to check it. And this time, there was when it froze, there was a small fracture in the glass tube, very small. The nucleation temperature changed to -5 degrees. No, I have -5, no, to 6.4 degrees as a result of that fracture. And it remained there. So the water is slowly leaking out of the tube, and eventually it leaked below that nucleation site, which is a physical, in this case, is a physical fracture in the tube. And then the water froze at -5.3 degrees, and of course, by this time we had lost all the water. So that's a case where we can change the nucleation agent. And this is another case. This is an old slide. Remember now, I'm reviewing, I'm not giving you new information, I'm reviewing my, quotation mark, contribution to water science, where you seal up a bunch of tubes, determine their nucleation temperature, and they are consistent. This is 13 runs, and you can see the error there. It's very consistent. That agent will cause nucleation at that temperature. This is statistically sound data, rock solid. I put my whole career on it. Now, you want to change it. So I take the vial out, shake it, boom. Some of them, if it's a physical nucleation site, it changes. Look at the change over here. There are several others. You shake them and nothing happens because you have not destroyed that site. That may have been a physical site. The other, it's like the one with the glass. And the others may be the fact that a particle was stuck to the side of the glass or something, and you dislodged it, and it changed the nucleation site. Now, another thing I can point out, take this bottle of water, cool it down, it'll freeze at, let's say, -2 degrees. Pull half of it out and put it in another container. One will freeze at -2 degrees, the other one may be at -5. Because the nucleation, it will freeze at the temperature of the highest nucleation site agent in there that dictates. So if you take that higher one out, it will move to the next lowest one, and the next lowest one, and the next lowest one. And that is why if you want to cool water down to -38 degrees, you have to do it in micro droplets, because the probability of an agent being in there has been reduced significantly because you kept removing them basically by decreasing the size of the water, of the sample of water. How am I doing on time over there? 3 minutes? Holy mackerel, I got carried away. Let me move on. This is just supporting evidence. Let me get to the real stuff. Upside down convection. That was the setup. we can make heat flow down a column of water simply by lowering the bottom of the column of water to below zero. We can turn it on and off simply by raising the bottom of the column of water to about zero, and the top of the column of water temperature goes to some much higher temperature, 30 degrees. This is speed talking now. So we set water up in a upside down convection state. We cool the water down. The whole column of water is cool, and we add a little bit of Bulgarian coffee to that column of water. We disrupt the upside down convection, and until that coffee is homogeneously distributed in the water, the temperature at the top of the column will remain up, and we see these thermal cycles in the water moving on rapidly. That's how we introduce it. I apologize for having to go so rapidly, but like most people, I came in with 2-minute slides. Now, this is new stuff. So we have clusters. These water clusters can communicate with each other. They're in resonance. We change the concentration of the clusters by adding, in this case, D2O to this cluster. This cluster can no longer communicate with it. Heat will not be transferred to it. It will find the way to a common cluster that has resonance, and heat will be transferred to that cluster. This one will remain at its existing temperature if this side is cold and this side is hot. And to cut really to the chase, this is an experiment that I would like to continue, but I didn't. I don't have time. In this side, that's just plain water. We've got a bunch of thermocouples here, 5 or 6 thermocouples in a row, in a kind of a circle there. We cool the water down, and it's a nice, smooth curve. We pick one thermocouple, and we subtract it from the others, and we get essentially zero. We have introduced a little bit of D2O, and look at what we get over here. More than as much as a 3-degree change. If one thermocouple is in this cluster of water that has the excess D2O in it, it will not receive heat. Its temperature will remain. The heat that was flowing from the other side will go into the thermocouple below. Its temperature will rise, and that's what we see right here. So that we have the ability to interrupt the resonance between clusters of water by adding a solute. It could be coffee, D2O, whatever we want. I am just about there. And this is a relatively new slide where you have a heat pulse in water, and you can look at the direction the heat will flow depending on the density of the water, whether you're above 4 degrees or below 4 degrees. If you're above 4 degrees, the heat will flow one way. If you're below 4 degrees, the heat will flow the other way. And again, I apologize for having to go so rapidly. So we introduced this solute, a D2O, into water. The adjacent clusters cannot communicate. We are cooling from the bottom so that water below 4 degrees won't arise. So it gets up to 4 degrees, but there are water clusters. So the heat can't transfer to the next water cluster. So that cluster now cools warms, and then falls back down. It cools and falls back up. So you have this barrier here at the boundary between the two conditions, and thermal cycles set up that will last for hours. And so I'll be finished here in a minute. So I see this thermal oscillation in the water around these thermocouples. So I hope you can read my writing on the slide there. This is new, so I decided this is interesting. what's the diameter and how stable is that thermal oscillation, is that oscillation there? So I take a thermocouple, as I showed here, put it on a motor-driven device, and I slowly lower it up and down this column of water. And so you can see the oscillation there in green. As I lower it down, I get to this circular convection cell, and I can actually measure its diameter, which is really, really beautiful from an experimental point of view. And one more. This is the whole thing just expanded. And so we have this cell that's circulating, move down through, and the diameter of the tube is 1 centimeter. And so the diameter of this convection cell is roughly 1 centimeter, vertical, horizontal. That is beautiful physical behavior of water. And finally, thank you. I apologize for taking a long time. Well, I apologize for having too much information.
No, it's okay.
But I kind of wanted to summarize.
Yeah, okay. Okay.
Well,
I share the enthusiasm of our chair. Some of these observations are amazing. I just want to ask a question about a phenomenon that you didn't comment on, but you showed. So we all learned that during the process of freezing, the latent heat is produced. However, it appeared from your slides that the latent heat occurs before the actual freezing, and we've confirmed the same thing. I wonder if you have some comment on this.
Yes, I think that is the initiation of it. I haven't been able to time it exactly, because you need, if in my case, if I'm with a thermocouple, my thermocouple need to be at that nucleation site to see how close they are together. However, your experiment with the infrared, if it was done in conjunction with the thermocouple, then you could, if we had a tube, for example, and you looked at the infrared and your thermocouple's over here, well, the infrared signal may come milliseconds or microseconds or whatever before you see it, and you could move your thermocouple back over near the nucleation site, and maybe they would come together. That's my...
It's possible. We've noticed a time difference up to a second or 2 seconds between the two. So from our results, the latent heat clearly occurs before the onset of freezing. So I just wondered, because you've noticed something rather similar, but you're not sure.
Yeah,
Okay.
I think the electrical EMF signal is produced initially.
Yeah.
That starts the process.
Yeah.
That's very fast, and boom, it's done.
Do you have an explanation for the electrical phenomenon?
Yes. Well, not a real explanation, but in terms of environmental configurations, suppose you have millions and billions of water particles in the atmosphere that are supercooled. And when the latent heat is released, they all produce electrical signals, so there's enormous charge spin up. And I suspect in that tube where I showed where the polarity of freezing was always the same, that there must be static charge in that glass, in my case, in that glass tube, and these clusters now respond to it. And I think it's a whole bunch of clusters rather than single molecules, because the consistency you get depends on the narrowness of the tube. In the very narrow tube, one end will always be positive, the other one negative. And if you have a much larger tube, you get some frustration there where you have both positive and negative on the same end. So I think this is a tabletop way that really we can discuss clusters.
Very amazing. Next question, please. Maybe I have a question myself, if it is possible. One last question. Do you think that using just out-of-the-box idea, do you think it's in principle possible to raise the freezing temperature
Well,
And the reason why I'm asking is
that-
in global
yeah.
warming, etc. No
that has
skating
been
anymore.
done. I'm a generalist, and I've worked with pyroelectric crystals. And if you don't know what they are crystals that develop an electrical charge by changing temperature. A group in Israel put water on top of a pyroelectric crystal and looked at the freezing temperature, and they slightly changed the temperature because of the electric field associated with it. But that was probably not applicable to anything other than a small
Maybe not yet.
system.
Okay. Thank you very much again.